So let that one go. All right. Sorry? No. No. All right. So I have a question for you that's pertinent to the lecture. Suppose you wanted to find out all the connected components for a graph. Or here's another context in which it might happen. You know that paint program when you click in an area and say fill, and all the pixels fill in with that color, and it just keeps spreading until it hits the boundary and fills in the whole thing? How do you think that works? What's a very efficient way to do that? Well, you could look at that as a kind of graph problem in which what you're looking for is if any two pixels are adjacent to each other, right, with the same background, then you want to count them in the same region and therefore assign them that color. So in a sense, it's almost like a graph problem as well, but in this case, they're quite highly organized in this grid, where each node is a pixel, and they have neighbors if the pixel is directly above or below or to the left or the right of the center pixel. So in fact, you could look at that as a graph as well. And what you're looking for is all those nodes that are connected, or all those pixels that are connected to the one where the click happened, because all those will count as part of the same region. Again, that's the same connected components. Now, if you think of it as two nodes are related to each other, that's why you put that edge between them, and you're asking, what are all the ones that are related to each other via one or more of these relations? That's known as a transitive closure, okay? So, transitive closure mainly because you normally think of it as, if you have, suppose you have some binary relation. You've learned about binary relations in COMP2211, I think, right? That thing that could be reflexive or symmetric. Remember that? All right. Some of them are equivalence relations, not all of them are equivalence relations. But suppose I just have a relation, so I have A relates to B. But I also have, and it's transitive. So B might relate to C, C might relate to D, B might relate to Z. By the time, if you're allowed to take the transitivity, apply the transitivity relation to all possible pairings, and then you would obtain this relation between all these different elements. You know, so for example, if A relates to B and B relates to C, transitivity says A relates to C. So the question is, what is the set of all things that are related to a node? That's what transitive closure is. If you keep expanding the set of things that are related to where you started from until you add no new nodes or no new, in this case, the edge means a relation, what you're constructing is the transitive closure of that node. So the question is how to do that. So that's it. It's all those values that are related to X. And what you want is, given pairwise relations, find all those elements. So the reason why this is a graph problem, so as a graph, it would be S comma E, meaning that S would now be your set of vertices. So you'd have a vertex per element that could be related, and you'd have an edge between any two as long as they were related to each other. Okay, so if that binary relation were adjacent pixels, then two pixels would be related if they were adjacent to each other. And then if you want a transitive closure, then that would give you that region of contiguous pixels. In other words, on that paint program, when you click, there will be a set of pixels that you need to color one color because they're all the same, connected to where your click occurred. So the question is, as a graph problem, what's a good way to find out what that transitive closure is? Any ideas? We've already covered a couple methods. In fact, that problem, security mesh, was an example of that, but it didn't need to be, we didn't need all pairs. We just wanted transitive closure of one node. In this case, what we want is transitive closure for all the elements in the set. Okay, so there's an algorithm called Warshall's algorithm, and it's quite neat. So n is a set of, let's set this up for a given graph. So n is the number of vertices, m is the number of edges, and what we're going to do is set up a matrix that looks kind of like the adjacency matrix, but it is going to have 1 in it if I related to J via transitivity. Okay, so we have that two arbitrary nodes have an edge between them if and only if they're related. And what we want is to compute the transitive closure of each node in V. So the idea is this: we're going to maintain a matrix what's a good name for this matrix? Let me call it C for closure. Remember that notation, C subscript n comma n means n by n matrix. Wait, that's not how you do it. Sorry. I'll do it like this. It's like this, bracket. Yeah, I'll just call it Cij. Cij n comma n. And I have to define what ij means, Cij means. So Cij is going to be 1 if I is related to j, and 0 otherwise. Now what we're going to do is initially we're going to initialize C to be the adjacency matrix. So we'll just have the so initially, all right, so let A be the adjacency matrix of G. So initialize C with A. So initially, these Cij's will just be exactly the binary relations that you're given. For example, two adjacent pixels. They'll be adjacent if they differ by one in one of the two coordinates, the x or the y coordinate. And what we want to find is all those other pixels that are reachable from it without crossing some boundary. So they all have the same background color to start with. So we want transitive closure. And so we initialize this matrix to be A, and here's the neat part. So this is where the Warshall's algorithm starts. It works with the observation that if I'll be related to J, if either it's already related, meaning you got it for free as I is related to J, meaning two pixels adjacent, for example, or if there's another K such that I is related to K and K is related to J, because that you get that through transitivity. That make sense? So here's the idea. We simply set up a loop that we're going to, for each entry of C, of course, this is not real code because I'm indexing from 1, I'm going to n. If this were Python, I'd be going from 0, 10 minus 1. This is more pseudocode, but it's easy to transform this. And here's the genius part. So the I and J keep track of which index we're updating. That K is going to loop through all the other nodes that there could have been. And so what we're going to do is just update Cij is going to be either what it was before, so it's good symbol for bitwise OR. Can I use that symbol? Do you understand that to mean bitwise OR? So either I is already connected to J, or I can reach K and K can reach J. That's it. That's the whole algorithm. What's the running time for that? Well, all right, first of all, why does it work? Does it make sense? So how you can regard this inner loop here is that by the time you've finished running this inner loop, you've tested all possible ways for I to be related to J via one link, don't it? That makes sense? And so in fact, what you'd have done at that point is you'd have improved for a single ij, you'd have now set the relationship for I to j dependent on whether it was possible to go via some other link to j. All right, let me there's a sorry? I don't hear the question. What was I saying about K? I actually think I wrote that loop wrong. Anyway, what was I saying about K? Because as I'm thinking about the reasoning, I'm like, wait a minute, that does sound bogus. What was I saying about? I was just saying that K is an intermediate, right? All right, so this is the index I and J, and what I'm doing here is checking. I'm going to update. I'm going to update the value at ij. It's going to be a 1. If it was original 1, that means it could have originally been connected anyway. Yes? But it should be related if there was another node that it could have been related via. So that's what this does. Either it's already related, or it can be related because I is related to K and then K is related to J. I have a problem with the loop though. That's why you see me hesitating. What's the problem? I have it inside out. Nobody wants that? The reason why, okay, what's the problem with this loop? You notice that once I do this once, I'm never gonna visit ij again. But is that valid? I mean, if two nodes are beside each other and then, those two are beside each other, I actually need to be constantly updating one of them. Provide at any given on the K iteration, we know I is related to J going through node numbered higher than K. So in other words, I is related to J at this point, at least either directly or via some node that's numbered no higher than K. That's the meaning of it. That means you've now gotten you have all the relations that I could reach J by either directly or through no node numbered higher than N. Of course, there are no nodes numbered higher than N, so therefore you have all the intermediates in that regard. Now, a simple adjustment to this idea. You see this OR and this AND? That has to do with the reachability, right? The transitivity is OR was there already. But actually, that pattern can be reused for something like shortest distance. And in fact, some other problems as well. But in particular, I want to focus on shortest distance. Suppose I want to know what the shortest distance is between two arbitrary points in a graph, not just from a single source. So Dijkstra's will solve the single source problem. But what if I need to know the shortest distance between any arbitrary 2 points? I need it quickly. I could rerun Dijkstra's from each node. That would tell me n times, remember how long Dijkstra takes? N plus n log n, right? So it would take me n times that. How long would this, how much time complexity is? Dijkstra's is actually n cubed log n. We can tweak this algorithm a little bit to get all pairs shortest paths in the following way. And when you do, so this is called Warshall's algorithm. The tweak is called Flloyd-Warshall. So if you wanted to know all pairs shortest paths, looks very similar. So maintain a matrix D. For the distances, we initialize D to be the weighted adjacency matrix. And we do the following. So for K goes from 1 to N, for I goes from 1 to n. For j goes from 1 to n. Of course, if you're in Python, you go from 0. And you update d as follows. So the distance from I to j, which is what d stands for, is going to be the one shortest distance, right? So either the distance you have now is the shortest distance, or, and remember what this means, up until this point, it's the shortest distance you know how, going through no node numbered higher than k. So either it is what it is already, or it could be shorter if you went via k. That makes sense? So either it is, so it's going to be the min of what it is now, dij, or the distance from I to k. What should I put here now? Plus the distance from k to j. That's Flloyd-Warshall's algorithm. Again, time complexity, order n cubed. And what this will do at the end, by the time this loop finishes, is you'll now have the best known distance from any node to any other node throughout the graph. Okay? Any questions? All right, so I'll see you tomorrow. Now we are now coasting into the final stretch of the course. The next topic, so we're leaving graphs behind. We're done with graphs now. The next topic is the very abstract, pretty complicated stuff, but we're just going to skim it. We're just kind of just fly by and say, oh, wow, okay. And the reason why we're doing that is so that you have an appreciation for it, because not everybody here is going to do theory of computation, and it covers material that conversationally, if you have a degree in computer science, people expect you to know. Notions of words like NP. Ever heard of that phrase? not capital N, capital P, not little p. Or what P means, or whether P equals NP. One of the biggest open problems in computer science is a set P equals NP. So things like that come up. The notion of NP completeness. Those are kind of buzzwords that are used in computer science. It's because you don't necessarily have to do theory, we need to cover it, just at least talk about it so that you have that in your vocabulary. So that's what the next 2 lectures in the course will be about. All right, so I'll see you tomorrow.